Okay, so this question is about reversible reactions and it's about energy changes. Reversible reactions. And it's about energy changes, and we talk about the enthalpy change, which we know can be exothermic when energy is given out, or endothermic when energy is taken in, when a reaction happens. So let's have a quick look here. This sign in the middle means that the reaction can go both ways. We can have a forward reaction going like this, and we can have a backward reaction going in the opposite direction. And you need to know that those both happen at the same time, and depending on the conditions, usually the conditions of temperature and pressure, you can either get more reactants or more products formed. And so the balance point will shift one way or the other way. Okay, sometimes it will go back to make more of the reactants, and sometimes it will go in the other direction to make more of the products. Now, if we're doing a reaction, usually we want to make more of the products because that's what we're trying to make. So when we're manufacturing stuff in industry, we need to pay attention to these things. Okay, so let's have a look at the question now. For reaction 1, predict whether the pressure should be low or high to give the greatest yield of products. So we're looking to maximize the products. Now pressure, whenever you see the word pressure, it's all about how much gas. If there's a lot of gas, then on one side of the equation, then the general tendency will be to move away from that, because high pressure reduces the gas, or wants to reduce the moles of gas. So what we've got to have a look at quickly is how many moles of gas are on each side of the equation in reaction 1. So let's do a quick count. So we've got 1 mole of CH4, we've got 2 moles of, well, it's water vapor or steam, so we've actually got 3 moles here on the left-hand side. How many moles do we have on the right-hand side? We've got 1 of carbon dioxide, and we've got 4 of hydrogen. So we've got a total of 5 moles. So we've got more gas on the right, so if we increase the pressure, the reaction will move to the left, where there is less gas. So pressure reduces the gas, moles of gas, so it moves to the left. So the yield will go down. Yield goes down. So the reaction will shift to make more reactants and less products, or fewer products, right? Give a reason for your choice. Well, I've kind of done all of that in the first part, but what you can say, left-hand side has 3 moles of gas. The right-hand side, RHS, has 5 moles. So increasing pressure shifts reaction to the left, where there's fewer moles. There is less gas, basically. Okay, now for reaction 1, predict whether the temperature should be low or high to give the greatest yield of products. So this is going to be whether energy is given out or taken in. So it's an interesting one. So let's have a look at the delta H. It's positive, which means it's endothermic, which means it needs energy. Overall, it needs energy, so it takes energy in from the surroundings. So raising temperature favors the products, because this reaction needs energy. The backward reaction is exothermic. So that gives out heat. and the forward reaction is endothermic. Okay, so endothermic reaction. So the one, when you raise the temperature, the one that needs heat, endothermic, will actually, let's put this, needs heat, will be favoured. And that means the reaction will shift to the right. So the reaction shifts to the right. Right, let's look at the next part. For reaction 2, suggest why changing the temperature will have less effect than reactions 1 and 3. So let's go back to the table. Okay, so let's look at the numbers. The difference between the reactants and products in terms of the heat is, or the enthalpy change, is very small here. It's minus 41 kilojoules per mole. And the others, there's a much bigger heat enthalpy change of reaction. So an effect on temperature. So since delta H for reaction 2 is smaller, any change in temperature has less effect. Okay. For reaction 3, predict the effect on the rate of the forward reaction of increasing the pressure without changing the temperature. So again, pressure, we've got to have a look at the moles of gas. So let's have a look at reaction 3. Reaction 3, count the moles. 1 mole here, 1 mole here, 1 mole here, and 3 moles there. So, if we increase the pressure, the reaction's going to move to the left where there's fewer moles. So, pressure, okay. So, pressure moles of gas, there's fewer moles of gas on left-hand side. So, forward reaction is reduced. But reading the question carefully, they're not talking about the yield on this one. They're talking about the rate. So the rate of the forward reaction. Now the interesting thing is that the rate of reaction will increase always at higher pressures. Because, why? Because a reaction rate depends on the number of successful collisions. And successful collision is a collision with enough energy to make the reaction happen, to exceed the activation energy. Activation energy. So when you've got high pressure, you've got closer particles. So if you've got closer particles, you've got more collisions. If you've got more collisions, you'll have more successful collisions. More collisions with enough energy. Right. Okay, the last part of the question, we've got to work out a little bit of a calculation based on what's going on here. The manufacturer makes a batch of ethanoic acid. You don't really have to know what that is, but it's what they're making. So you can see that CH3COOH is ethanoic acid. We make it from methanol and carbon monoxide. He starts with 64 kilograms of methanol. Well, the first thing to do is look at the moles. Count the moles. On the left-hand side, what have we got? We've got 1 mole of methanol, and 1 mole of carbon monoxide makes 1 mole of ethanoic acid. So left-hand side, we have the 1 mole of methanol produces, on the right-hand side, 1 mole of ethanoic acid. Right, so however many moles of methanol we've got, we will always produce the same number of moles of ethanoic acid. So we've got to use the triangle where we've got the number of moles here down the bottom, the mass of what we've actually measured in the laboratory, and then the relative formula mass of methanol. So let's have a look at methanol. MR of methanol, CH3OH, is C is 12 plus 3 hydrogen, 3 times 1, plus the oxygen. How many oxygens do we have? 1, so it's just 16, plus another hydrogen, 1. So we add all these guys up, and what do we get? We get 12 plus 3 is 15, 1 is 16, and 16 is 32. So this is equal to 32 grams per mole. Right, so how much mass did we actually have? We had 64 kilograms, and we've just worked out that it's 32 grams per mole. That's what MR is. So how many moles do we have? Let's have a look at this. How many moles do we have? N equals 64 kilograms divided by 32 grams per mole. Now I'm going to convert it all to grams. So 64,000 grams divided by 32 grams per mole. I'm going to do that calculation, pop out my calculator and just go 64,000 divided by 32 equals 2,000. So 2,000 moles. So that means we'll have 2,000 moles of ethanoic acid. So then we've got to use the triangle again and say, let's draw it out again. Draw it out again up here. And this triangle, what we're actually trying to do is work out, let's put these things together, work out the mass. So we need to find the molar mass of ethanoic acid, which will be 12 plus 3 times 1 plus another 12 plus 2 times 16 and 1 hydrogen. So let's add all these guys up. 12 and 12 is 24 and 32 is 56 and 4 is 60. So MR of CH3COOH equals 60 grams per mole. So how much mass have we got? Well, we've got 2,000 moles, which is the N, times this. So let's just work out the mass is equal to N times MR equals 2,000 moles times 60 grams per mole times 60 equals 120,000 grams, which is equal to 120 kilograms. And that's the maximum mass we could get. And that's the question.